Okay, good morning all and happy Vasant Panchami to all of you. And today I'm going to deal with the mathematical aspects of thermodynamics. It will be an interesting session, so please watch the full video for your benefit and to enlighten yourself in science education. And here we go. The idea of thermodynamics is not a new one. It dates back to ancient days. So fundamentally, this entire structure of thermodynamical science is concerned with conversion of heat into work and vice versa. Now let me give you a very simple example. You burn coal, heat water, create vapors, make a turbine to let pass vapors through it. As the vapor is passing, the turbine wheels will rotate. Connect that with a big magnet. Rotation of rotor will create rotation of magnet. Changing magnetic field will induce a current in the wire. The induced current will come to your home and you pay electricity bill. So this is a very simple story behind burning coal and paying for that. So basically you are not paying for the electricity, you are paying for the coal that is being burnt here, or paying for the hydro energy that is harnessed here, or paying for the windmill which is being set up here to create that rotor movement. Now of course the laws of thermodynamics cannot be proven because it's an experiential science. It's directly based on the observation of this great fundamental cosmic nature. Just to sum up the first law of thermodynamics, as all of you already know, is basically law of conservation of energy, which says energy can neither be created nor be destroyed. It can be just transformed from one form to another, and that's a very big statement. The second law puts a directional constraint on the happening of nature. So second law tells, like most of the natural process are spontaneous. Like it will happen of its own. For example, you take a apple, leave it, it will just fall. So it's a spontaneous process. Can you undo the apple experiment? Of course, yes. I can take an apple, I'll let it fall, I can put it back to the original configuration to a particular height from where I let it fall. Okay. But so even if an apple can be reversed in its path, or the process can be reversed forcefully, or maybe in whatever means, there will always be a directional constant on it. Although the system can be restored to its initial position, but the surrounding must have suffered a change while doing any process. And that's the beauty of second law of thermodynamics. To appreciate it, let me give you one more fundamental example. Let's say we have a rotating wheel, a wheel rotating at, let's say, very high speed. Now with the application of a brake, or we can just, of course it's dangerous to touch it. So you can just touch it with a cloth, so you can just stop it with a very, like rough cloth. So basically cloth will create friction and the entire kinetic energy is getting converted into heat energy because heating can be sensed there. Now can we reverse the process? So the kinetic energy made its temperature of the wheel to increase as it is stopped. Now is it possible, like I cool down the wheel and it starts rotating, like it starts rotating in the opposite direction? Of course it will not happen. So there are many processes in nature which is spontaneous and which happens in both directions. There are many processes, even if you wish, still it cannot happen in both directions. Okay, so there must be a directional constraint to the happenings of natural process, and that is basically dictated, that is basically captured and capsuled and shrouded in the second law of thermodynamics. And in fact, that's a gateway for birth of entropy. Now the definition of thermodynamic scale itself is an interesting thing, like how from Celsius scale to Kelvin scales things were made, and it's a pure mathematical journey, which I'll not go much deep into this because of the time restrictions, but here we start with the entropy, and as we know, we'll talk about the heat engine first. What is heat engine? Heat engine is a mechanism or is a machine which operates in cycles such that it derives heat from a higher temperature T1 and it throws heat to a lower temperature T2, and by doing so it generates work W. Of course, T1 is greater than T2. Now this heat engine can be reversible heat engine in the ideal situation or irreversible. Practically, you can't have a reversible process because reversibility is an idealism. The reason being, if delta T is exactly equal to 0, if there is no temperature gradient, the process cannot work. So there is no process which can come out of 0 temperature gradient. So in the limiting case, we can conceive reversible heat transfer or any reversible cycle consisting of reversible processes as a very infinitesimally small temperature gradient or infinitesimally small concentration gradient or pressure gradient whatsoever. For instance, you can think of a temperature 20.000001 degree Celsius in the limiting case, and now connect with the reservoir with 20 degrees Celsius. So of course the temperature gradient is tending to 0. So now the heat transfer that is achieved over here can be conceived as reversible heat transfer. But practically, let's say we have 20 degrees Celsius and we have 10 degrees Celsius. And if I just connect this with the conducting wall, so heat will transfer, and by doing so, this is completely irreversible heat transfer. Why it's irreversible? Because even if from 10 degrees Celsius to 20 degrees Celsius, you can heat it back, right? By heating it back, I can bring the system to the same configuration by from 10 degrees Celsius to 20 degrees Celsius. But the surrounding has suffered a change. Okay, but the surrounding has suffered a change. How? Because to bring 10 degree to 20 degrees Celsius, now work has to be supplied here. And who will supply the work? Heat pump. Okay. So you have to take the help of an external agency to reverse the process, and hence it's known as irreversible process. So irreversible processes are not those which cannot be reversed in the path. Of course it can be reversed. Okay, I can heat a body, I can cool it down. Again, I can heat it and cool it. Is it a reversible? No. Because when you are raising the temperature from lower temperature to higher temperature, it's not going to be as spontaneous the way it is from higher temperature to lower temperature. So in the later case, we have to use heat pumps. So the first part was spontaneous, it's happening by its own. For the second part, it's not happening by its own. We have to supply an external work to the system. And in that sense, although the system has restored its initial configuration, the surrounding has suffered a permanent change. And that's an indication of irreversibility. So all these philosophies captured very nicely with beautiful mathematical equations, whether it's Carnot engine, Carnot cycle, efficiency, coefficient of performance for refrigerator, or maybe if I can recall, it's Clausius inequality, entropy, law of increase of entropy, and many more. Okay, so here we go. Let's come back to our heat engine, and we know an heat engine operates in a cyclic process, a continuous cyclic process which derives heat from a source reservoir with temperature T1 and throws it to a sink with temperature T2. Now some of you might feel like when you are taking heat from this, let's say Q1 heat is taken from T1, the temperature should go down. Of course it will go down if we'll have a finite objects, but here I am taking the source to be infinite reservoir with heat capacity to be infinity in ideal case to start with, and which you can conceive as an environment, because even if you heat some part of environment, the overall temperature of environment is still gonna be constant. Now according to first law of thermodynamics, if I apply here, Q1 uses some part of it to deliver work and other part is thrown in the sink. So Q1 equals W plus Q2. Now the beauty of this equation is, this is first law of thermodynamics. What second law of thermodynamics tells it, you can never achieve Q2 equals 0. So this is never possible. Q2 can be 0 according to first law of thermodynamics. So first law of thermodynamics is still allowing Q2 to be 0. But the second law of thermodynamics is giving very strong physical restrictions on the heat delivered to the sink. What it means is practically it's never possible that you have a heat engine which operates just on one single temperature. Like you derive heat from the temperature T1 and throw it to the same temperature, or maybe you don't throw it. because if you don't throw it, the heat engine starts, like heating up, and definitely it will stop working immediately after it attains the same temperature. So to get continuous supply of work, there has to be a source, and continuously you have to sacrifice something in the form of heat given to the sink. Okay, so from here the efficiency as given by Carnot is what we want is work divided by what you sacrificed is the heat Q1, and W is Q1 minus Q2 by Q1, which simply goes to 1 minus Q2 by Q1. Now it can be shown, and that's not obvious, it's not trivial at all, that Q2 by Q1 will be equal to T2 by T1, where T1 and T2 is a thermodynamic temperature scale, it's absolute temperature scale. And later it can be shown like this temperature is basically same as the ideal gas temperature, which you are using in PV equals nRT. Okay, so this is not something you should take for granted. If I use an absolute temperature scale, or moreover, the ratio of Q2 by Q1 is same as the ratio of two temperature function, because it was shown by Carnot that for a reversible engine, the ratio of heat or Q source by Q sink will be a function of temperature of source and sink. Now it's simple mathematical calculation. In linearity of this f of T1 and T2, it can be proved like this ratio is same as T1 by T2. So this T, which is absolute thermodynamic scale, is some function itself of T1 and T2 if they were in Celsius scale. Okay, so that's a definition in fact of temperature. Once we realize this definition, now things becomes very obvious, because Q1 by T1 minus Q2 by T2 from the above equation is 0. It can be written as Q1 by T1 plus minus Q2 by T2 equals 0. What does it mean? It means Q1 by T1 value, Q by T value is special, and in the entire cycle, this Q by T value, this cycle, of course for reversible cycle, we have derived this, is equals 0. So put in a very nice fanciful sense, let's say if there is a small temperature difference between this, and that is the concept, let's say we are operating heat engine between T and T plus dt maybe. So I can tell a small heat transfer dq over the temperature T in a reversible cycle equals 0. Now that's something really magical, because del q by T is a perfect differential. It's perfect differential not because we have defined it like that, but because of the very law on which the efficiency of Carnot cycle is based. Because for integral of something to be 0, let's say integration of dx to be 0, it must be from 1 to 1. Okay, so if you are moving in a cycle from the same path from one point and again back to the same point, of course its integral will be 0. So that shows del q by 2 is a perfect differential. So hence I am tempted to write this as some quantity, let's say dx. Right, now what is dx? What is this quantity x? That we don't know. It is maybe some physical quantity associated with the system, but what I know is a perfect differential. Now in the language of mathematics, you can see like del q dependent, it's a path function, right? So del q is not a perfect differential. It depends on the path, whether it's isothermal process or adiabatic process, q will keep on changing, right? But del q by T is a perfect differential. It means 1 by T is acting as an integrating factor, right? In the language of maths. Okay. Now mathematics, those physicists has defined this x as S. They call it entropy. And this is the part of entropy. So by definition, del q by T, of course in a reversible case, I'll define a new state function as ds. And by this, I can tell del q reversible by T in a cyclic process equals 0. It means delta S in a cyclic process has to be 0 according to our definition of this. Let's apply to this. And okay, so before we go further, what happens when we have irreversibility in the system? So is delta S process dependent or path dependent? Of course no, because delta S, how we have defined, is del q reversible by T from maybe from path 1 to path 2, right? So S2 minus S1 can be defined via reversible path. Even in the irreversible case, delta S value can be defined via reversible path. Then what is the difference between irreversible and reversible path? Let's say we have again a reservoir at a temperature of 30 degrees Celsius, another reservoir at the temperature of 20 degrees Celsius, and we have a heat engine. For the sake of clarity, I'm taking two cases. Let's say it's a reversible heat engine, another is irreversible. So this guy is irreversible and this is reversible. And this time, let's say heat transfer is Q1, Q2, whatever, Q3, Q4. In the case of reversible heat engine, Q3 by Q4 will be just a function of temperature. Of course, not in Celsius, so it will not be equal to 30 degrees Celsius by 20 degrees Celsius. You have to convert into absolute thermodynamic scale, which is Kelvin 270 plus 30 by 273 plus 20. Okay, so let's call this temperature to be T1 and T2 in Kelvin, absolute thermodynamics temperature. So Q3 by Q4 is going to be T1 by T2, right? But in case of irreversible engine, let's say it's T1 by T2, here Q1 by Q2 is not equal to T1 by T2. And that's a major difference between when you are operating a reversible cycle or reversible engine with all cyclic process as reversible or irreversible. So I hope this concept is clear. Now some of you might feel like how a reversible cycle is possible, because all the cycle is reversible, all the process within the cycle is reversible, but heat transfer is happening at the finite temperature difference. No, basically it's happening because let's say in the beginning you were having 30 degrees Celsius. So each and every process of reversible engine itself is maintaining a very small temperature gradient with that. Okay, so maybe the temperature you can conceive like the first heat transaction was happening at 30 degree and 29.999999 degrees. It's like cascading of a small beakers are there in trillions and trillions amount with temperature 29.99, 29.98, 29.97 and so forth. So you can basically conceive the reversible heat transfer as cascading of, like infinitely many heat transfers with delta T Clausius inequality, which tells for any reversible cycle and operating between two temperature range, the heat ratio is same as their absolute thermodynamic temperature ratio.